Tonight is one of the most spectacular meteor showers of the year, the Perseids.
And if it's clear, despite the moon, you should be able to see a number of shooting stars streaking across the night sky. And just think about this. Every time one vaporizes in the atmosphere, a small part of that meteor can fall to Earth as dust.
In fact, this all adds to the 40,000 tons of space debris and dust that falls onto our planet every year. 40,000 tons. And so tonight, from here at the Norman Lockyer Observatory in Devon, we're going to investigate the strange stuff that comes from outer space.
Just think about that 40,000 tons for a moment. That means around 50 times more stuff falls from the sky every year than fell from the cliff in this landslide just down the road in Sidmouth.
That sounds alarming, but most of this space debris is nothing more than dust, tiny particles that waft gently through the atmosphere, each no larger than a sand grain. Slightly larger particles burn up on the way in, producing spectacular shooting stars, or meteors.
Tonight, we'll find out how Earth's history has been shaped by this space debris in surprising ways, and how some of it can be found on every rooftop in the land.
One of the remarkable things about cosmic dust is these tiny little particles have the same composition as the solar system as a whole.
Wow.
We'll see how scientists are working to make sure that we're prepared for the threat of a rogue meteorite hitting the Earth. Pete explains the best ways to see the Perseids, and he meets an astronomer who's found a way to see these meteors in the daytime. Fortunately, large objects that might make it down to the ground, meteorites, are pretty rare. There have only been a few recorded falls in British history. But smaller objects are falling around us all the time, bringing with them new and surprising information about our solar system's past. These are micrometeorites, nothing more than cosmic dust. And this stuff is all around us all the time, in the air, settling onto the ground, landing in our gardens and on our roads. In search of this valuable dust, Maggie climbed up onto the roof here at the Norman Lockyer Observatory, along with micrometeorite expert Matt Genge.
Matt, I do have to ask, what are we doing up here on the roof?
Well, we are up here to look for something quite incredible. We're looking for cosmic dust. And usually I have to go to the Antarctic. But we've actually discovered that because it falls all the time, everywhere, about 1 particle per square metre, that roofs like this are perfect little collection plates for cosmic dust, because they fall on the roof and then they get concentrated by the rains in gutters.
So shall we see if we can find some?
We'll give it a go. We'll give it a go. So there's a nice little gutter here. This is going to be highly technical.
Right, OK.
So I'm going to start off by using a spoon.
So it just looks like the sort of things you do find in the gutter?
Yeah, it's nothing special. Actually, a lot of it's going to be algae.
Ah, yes.
There's going to be a lot of terrestrial wind-blown dust. And some of that will be natural. So for example, you end up with dust from the Sahara on the roofs in the UK. But a lot of it's also going to be artificial.
Oh, so how will you be able to identify the cosmic dust out of all these different materials?
Well, the cosmic dust is heated as it comes through the atmosphere. So it burns up as it comes through the atmosphere.
Like a shooting star, it sort of burns up in the atmosphere?
Absolutely. And they end up as tiny little magma droplets. So they're perfect little spheres. So we're going to be looking for that shape. But more importantly, they contain magnetic minerals. And that means we can use a magnet to separate them from a lot of the terrestrial debris.
Fantastic. Well, let's get started.
Yeah.
We'll return to Matt's experiment later, when he's had time to process his potential cosmic dust. Meanwhile, more on the highlight of this week's night sky, the Perseids. and Pete's here to show you how to get the most out of this glorious meteor shower and how to see it even in the daytime.
The Perseid meteor shower is one of the astronomical highlights of the year. Now, activity starts about mid-July, but reaches its peak on the nights around the 12th, 13th of August. This year, we've got a bit of a moon, which is going to mess up some of the display, and it'll knock out some of the fainter meteors. But if you go outside and it's nice and clear, you should still be able to see the brighter ones, and they can be pretty magnificent.
The Perseids all appear to emanate from a small area which starts south of the constellation Cassiopeia and shifts eastward over a few weeks into Camelopardalis.
Make sure you're in darkness for at least 20 to 30 minutes so your eyes can properly dark adapt. Now, if you intend to use a torch, a good tip is to use some red gel over it so that it looks red and it doesn't destroy your dark adaptation. Now, the best time to view is after 1 AM BST, because after that time the Earth will have turned, so we're hitting the meteors head on, the energy of impact is increased and the meteors appear brighter.
The Perseids are actually the remnants of Comet 109P Swift-Tuttle. Each flash is caused by a tiny piece of rock called a meteoroid, typically between the size of a grain of sand up to about the size of a golf ball.
A meteoroid trail is actually the site of some interesting science, because a meteoroid doesn't burn up in the atmosphere, it vaporizes. Now, as the meteoroid passes through the atmosphere, it compresses the air ahead of it, and that creates a huge amount of heat which vaporizes the front surface of the meteoroid. Now, you can see how this happens with this glass piston. There's a little bit of lint in the bottom, and the piston is sealed. When I press this plunger down, we get a flame.
By compressing the air in the piston fast, I've raised its temperature hundreds of degrees, so hot that the lint spontaneously combusts. As the meteor vaporizes, it sometimes leaves a trail of colour in its trail. The colours depend on the makeup of the meteoroid and the gases in the atmosphere.
Sometimes, when you get a really bright meteor trail streaking across the sky, you get what looks like a smoke trail left behind it, and that's known as the meteor train. Now, it's not a smoke trail at all, it's a column of ionized gas, and if it's there for long enough, the high altitude atmospheric winds can blow it about, so you can see it distort in the sky as you watch it. There is another technique which can be used to see these incredible events, a technique which amateurs can use to see hundreds more meteors than they would normally, even during the day.
Amateur Mike Dennis is able to spot meteors from indoors. He uses radio waves.
So this looks interesting. What's going on here?
Well, we have a VHF signal that goes up into the sky.
Right.
And when a meteoroid enters the Earth's atmosphere, and as it's burning up, it generates ionisation that we can reflect radio waves off of.
Right, OK. So you're detecting the trail left.
Yes. These are very short little pips.
So each one of these peaks is actually a meteor?
Just tiny specks of dust. You wouldn't see them visually.
Oh, there's one. Wow, look at that, yes. So that's a... I guess you're going to say, you're going to bring me down now and say that's quite a small one. Which
that is quite a small one. You wouldn't even see it, but
right.
That is a larger speck, about the size of a grain of sand.
Right, OK.
Probably even smaller.
That's a big one going off there.
Yeah, you can see now that this one was faster when it...
right.
Although it produced less energy, it actually came in faster.
OK. So when you get an event at night, can you tie that up to what you see visually?
We certainly can. And I've got an example here.
OK.
And you can see this is a meteor that's happening on this building. That's first from our north camera, then from the east. And this is the radar screen event that happened. This is the actual event that you just saw. This is another meteor that came after it.
So with a shower like the Perseids, what would that actually look like?
At the peak of the Perseids, this is last year's peak.
Wow, OK.
And it can get very, very busy.
So if people wanted to set this up themselves, is it difficult to do?
To set this up as we've done it, it would be very difficult. But if you just want to experiment with listening to meteors, you can use even something as simple as an FM broadcast radio.
Right.
During a busy meteor shower. So long as there is an out-of-range radio station on that frequency, when a meteor happens, the radio wave will bounce off the meteor in the same way that
so
we
you can
are.
hear it.
And you'll hear, for a brief moment, you'll hear that for about half a second to a second, sometimes longer.
That's actually
You'll hear that coming
brilliant
and going.
because, I mean, the thing which clobbers us all the time in the UK, of course, is the cloud cover. So with that, you can actually effectively hear a meteor shower throughout the day.
Yes.
Fantastic. Well, thank you very much for your time.
Thank you.
We learn a lot about meteors from watching them in the sky, but even more when they land on Earth. Objects which do that are known not as meteors, but as meteorites. Earlier this year, we had the chance to see one of the largest collections of meteorites in the world. Perhaps surprisingly, that collection belongs to the Vatican Observatory. Maggie saw some of the highlights, guided by the collection's curator, Brother Bob Mackey.
So, Brother Mackie, how big is the collection?
We have 1,200 specimens here, representing all of the different meteorite types. The vast majority of our collection are ordinary chondrites. These form the majority of the meteorites that fall to the Earth. These are primitive meteorites that are 1,000 million years old. And so they still contain tracers of the origin of our solar system. They're older than any rock you'll find on the Earth. This is an important historical sample right here. This is a specimen of L'Aigle, which fell in 1803. It fell in France. This was the first meteorite fall that was well documented by scientists of the era. So it represents the recognition among the scientific community that meteorites actually are rocks that fall from space, that they have an extraterrestrial origin.
Oh, wow. And so you've got the chondrites, these are the common chondrites. What other types do you have?
There are carbonaceous chondrites, which are also very primitive, but formed in a different part of the solar system. This is a very rare type of carbonaceous chondrite called Orgueil, also fell in France in 1864. And these have been very precisely dated to 4.568 thousand million years in age. And this gives us the best estimate we have for the age of our solar system. This is an iron meteorite. It is made of solid iron nickel.
You can see all the crystal structure. It's amazing.
Yes, it's called the Widmanstatten pattern, and it's because there are two different alloys of iron and nickel, one with a little more nickel, one with a little less nickel, and they form together, and they form this pattern.
Yes, beautiful. What else have you got?
This is a specimen of Chelyabinsk, which fell over Russia in 2013. When it exploded into hundreds and hundreds of pieces. So the original object would have been possibly perhaps as large as this small room here, this closet.
So you have this amazing collection. What science do you do with them?
Here we study meteorite physical properties. Density, the porosity, which is the amount of pore space, and heat capacity, which is the amount of energy it takes to change the temperature of the meteorite. It's a very important property for understanding the asteroids that they came from, how they behave when they interact with each other or interact with the sun. For instance, an important effect is called the Yarkovsky effect, which as the sunlight heats one side and as that energy re-radiates as the asteroid rotates, it can actually change the orbit or the spin rate of the asteroid. Many people who study that specific effect, but to understand it better, they need to know what the heat capacity is.
Yes. And that's what you measure here?
That's what we measure here.
Thank you. Studying meteorites can tell us about the solar system. But some scientists believe they can also tell us a lot about the Earth. Scientists now believe that this steady rain of stuff from space has influenced our atmosphere, our geology, and even our weather. And possibly life itself. Dr. Penny Wozniakiewicz is at the heart of this new research into the role larger meteorites have played in Earth's evolution. Her team at the University of Kent have built a massive gun and are using it to model how meteorites could produce unique compounds they smash into the Earth itself.
So in the lab, we take an object that we know really well, we accelerate it to high velocities into any target that we're interested in. So for example, here we have an aluminium plate that's been impacted by something only a few millimeters across,
Wow.
but at 7 kilometers a second. And so you can see that the impact crater that it's produced is much bigger, and that's down to the sheer energy of the impact process.
And it really does look like a crater. It looks like something you might see on the moon, with the rough edge to the crater there.
Yeah.
So what's going on with these impacts? What are the results?
After we impacted, we found that we had produced impact melt, so stuff that had solidified and, well, quenched as a glass. But we also found within that we had crystals that seemed to have kept the original composition, but changed their structure. So their atomic form had changed under the pressure and temperature of the impact.
So these are quite profound, detailed changes to the composition of these bodies.
Yeah, so you get the production of what we would see as exotic materials during these impact events.
And so if we think about what meteorites might bring to a planet, particularly in the early days, it's not just about what's in the meteorite, it's about what can be produced when it hits.
Absolutely, yeah. And there's been some very interesting research done recently looking at whether you can actually produce more interesting organics, so things that might be interesting for life.
So quite complex molecules.
Complex molecules, yes.
So if that's the case and these things happen on impact, we know there was a time when Earth was hit by lots of these small bodies. So could some of the stuff we see around us on Earth come from impacts?
Yeah, I think some of it could have been generated by the impact event itself, and some of it could have been brought by the impacting object.
It's a fascinating idea. 4 billion years ago, basic organic materials, the very stuff of life, might have been created by the impacts of meteorites. And those meteorites might have changed Earth's destiny in other ways too.
There are theories that some of the water on Earth actually accreted as part of the original Earth. Another thought is that water was also brought in at a later time by comets and meteorites, asteroids.
You would have had a lot of impacts, though, surely, to create enough water on the Earth.
Yeah, and there were a lot of impacts in the early history of the solar system. So, yeah, the water could have come from these objects.
So Earth's water might have come, at least partly, from asteroids and comets. But what else might meteorites bring down to Earth?
So meteorites can also bring things like organics to the Earth's surface. So a particular example would be the carbonaceous type chondrite meteorites. These have quite a large proportion of organic materials within them. A very notable example is the meteorite Murchison. This one is often referred to as, if you smell it, you can smell like a solvent smell because of the organics that it contains.
You get smelly meteorites.
Smelly meteorites, yes.
And that's because of the complex chemistry that's inside.
Yeah, exactly. These can be a whole range of organic molecules within them, so including carboxylic acid, amino acids, amines, alcohols, sugars, a whole range.
So those are, you don't want to jump to this, but they're the building blocks of life. They're the kind of things that biology uses.
Exactly, yeah. They are the precursor chemistries that you need for life to thrive.
It's an amazing thought that the ingredients that produce life on Earth might have come from space.
It's mind-blowing, really.
It's fascinating stuff.
Yeah.
Thank you very much.
Thanks.
Meanwhile, in our makeshift laboratory, Matt Genge has been preparing his sample from the rooftop. Having dried it in an oven, he sieves it and then passes a magnet over it, pulling out anything magnetic. He then places this material on a slide and puts it into an electron microscope.
So we can see, actually, all these really dark things on here, they're probably bits of algae with some wind-blown dust in. And what we're really interested in is the really bright stuff, because that probably contains lots of iron.
So there's one there, but I guess that's a bit too irregular.
This one's very angular, so that's not melted. I suspect if we'll look at some of these little bright spots.
Now, what's the probability of finding a cosmic particle?
I'm afraid it's actually quite low.
So the odds are against us.
The odds are against us, but we will do our best.
It just looks like we've got a few candidates.
So there's a nice one here just below the middle, and let's try and get that one right into the middle, and then I can increase the magnification.
Okay, so we're going up to sort of 150 times magnification now.
Yeah,
200.
Actually, it's not looking too bad. It's certainly.
Actually, it does look quite spherical.
It does look pretty spherical. Let's go right in.
Okay, 1,000 times magnification now. This is amazing. Yeah.
Actually, it's looking surprisingly good, but it's a perfect little sphere.
It is. Yeah, with a sort of a small nodule on top.
Yeah. Actually, the nodule's good because many of the micrometeorites like this have these little protrusions from the side. So actually, that's looking really good. It's definitely a potential. We've got to be slightly careful because there are molten droplets that we produce, artificial droplets.
So how can we tell the difference?
Well, there's these wonderful little crystals on it. Can you see these lines on the surface?
Yes, like striations or something.
We call them dendrites. And they tell us that this was molten. So this was maybe at a temperature 1,500 degrees C, and then cooled very rapidly. And that's what happens to meteors during atmospheric entry. They burn up, and then they cool down really quickly. So that all fits quite nicely. To be sure, though, I think we need to... We'll do a chemical analysis on that.
And we can do that with this
We can do that with this machine. So what we're seeing here is that there's lots of iron in the particle. Yes. There's lots of oxygen over here. So that means it's an iron oxide mineral. There's some silicon and aluminium, but these particles tend to absorb that when they're sitting around in all this water and algae and...
Yes, on the roof up there.
On the roof for a long time. So it's mainly iron oxide, and that's actually really good, because this isn't prepared at all, really. It's just come straight off the roof into an oven and then straight into the microscope. So to have such an incredible image as this is actually really exciting. So I'm really quite sure that this is a really good possible micrometeorite, you know. So I'm 95% sure this is a micrometeorite. So
and that's really against the odds.
It is really against the odds. I am actually really excited by this because I wasn't expecting to find anything on this roof at all.
Yes. Well, that's fantastic. So what does this particle tell us about the early solar system?
Grains like this, if this was one of those primordial grains, they actually form in stars, in the outflows from stars. So we could be looking at you know, a stellar dust particle that has survived 4.5 billion years to be collected on a roof.
In Devon.
In Devon.
Yes. Well, it's an amazing find and a wonderful story. I wasn't expecting to see anything, so it's brilliant to find one. It really is a remarkable find. A genuine micrometeorite, possibly older than the solar system itself, from the mud found on a rooftop. And all the more amazing because of its size, less than the width of a human hair. Of course, space debris of this size is generally harmless. It floats gently to the Earth. But when the debris is larger, the outcome can be much more alarming. To understand why, we need to think of the energy involved. Your average Perseid is an object about this size, travelling at 30 kilometres per second, far faster than a speeding bullet. And if we scale it up to something the size of a brick, when something this size hits the atmosphere, it releases the equivalent of 1 ton of TNT. And many are much, much larger than bricks. 2013, a 300-kilogram meteor explodes over Chelyabinsk in Russia. The blast it produced was so powerful that it shattered windows over several thousand square kilometers. And there's plenty of evidence of even larger strikes too. In Siberia, trees were flattened for hundreds of square kilometers after a meteor airburst in 1908. This is the famous kilometer-wide Barringer meteorite crater in Arizona. And in the Yucatan Peninsula 66 million years ago, scientists believe there was a supermassive impact. This radar image shows evidence of a huge crater edge, now buried deep underground. This, of course, was the KT impact, the dinosaur killer. Chris met asteroid expert Professor Alan Fitzsimmons to gauge the real risks of a large meteorite impact.
How big a threat are asteroids to life on Earth?
Well, they're a threat, certainly. If we go back millions of years ago, we know that mass extinctions on Earth have been caused by asteroid impact, and the famous one being the KT impact, which helped to at least wipe out the dinosaurs.
So how are we doing? Could there be a dinosaur killer out there?
Well, the good news is because the dinosaur killers, as we call them, are so big, we're talking objects that are 10 kilometers across. We can see those from a long way away, and we believe we've catalogued all of them. They're only a handful. We know where they are. They're not going to come anywhere near the Earth anytime soon.
Okay, so any dinosaurs they can relax.
They're fine, they're fine.
But we've seen you can get damage from smaller objects.
Absolutely. In fact, even if you go down to a 1 kilometer diameter asteroid, there's models that suggest that could still set off significant casualties around the world because of the environmental effects from the impact. Up to perhaps 25% of the world's population dying from starvation due to the failure of crops in farming around the world.
I hope the next line is, I know where they all are.
We know where 90% of them are. So we think there's roughly 1,000 of them, and over 900 have now been found. And as the surveys continue, we should sweep up most of the rest of those in the next 10 or 20 years. But we have a class of near-Earth asteroids we call potentially hazardous asteroids. And these are asteroids that can pass within 7.5 million kilometers of the Earth's orbit. So they come as close as that or closer. And we believe initially that they could be 140 meters across or larger. And we have that size limit because we know that no matter what the asteroid is, calculations show that if it enters the Earth's atmosphere, it's going to make it to the ground.
Okay, so that's the difference between a spectacular shooting star and something we should
Absolutely. 140 meters across is when you worry because you know no matter what it's made of, it's going to reach ground level and it's going to make a crater and the effects will be multiplied.
So what's next? We found a potentially hazardous asteroid. We think it's pretty big. We think it might be on a collision course. We've got an initial orbit. Does this get kept quiet or do we announce immediately?
Well, the important thing to realise is that everything is public, everything is announced, and we need that because when you discover a potentially hazardous asteroid, you need everybody that can observe it to observe it so we can pin down the orbit better. And so everything is public.
And so are you worried? Are there objects that you know about that might hit us?
There are no significant worries at the moment. But we've got to remember that if we go to the size range of potentially hazardous objects, anything 140 meters across or larger, then there's probably about 20 to 30,000 of those that exist at the moment. And we've only found 8,000 of them. So we've only got about 30% of that population. And even when we do find them, quite often the orbits are uncertain. If we go down to smaller sizes, such as the Chelyabinsk or the Tunguska impacts, all bets are off. These things are random, they're like buses. Sometimes they won't turn up, sometimes you can get two very closely arriving at the same time. So, who knows? We could be hit by one as people are watching this programme.
Well, there's a cheerful thought. Alan, thank you very much. I hope you make it home safely. Well, don't let that thought deter you. Do go out right now and try and see tonight's Perseid meteor shower. It really is one of the astronomical highlights of the year.
Don't forget to watch us again next month when we'll be telling the incredible story of Cassini, one of the most successful space explorations ever. And as it reaches the end of its mission, we'll be asking what questions has it set us for the future.
Meanwhile, don't forget to check out our website for more content from this month's packed show and for our star guide, which includes information on how to spot asteroid Florence as it skims past the Earth in September.
And of course, get outside and get looking up, especially if it's clear. Check out those Perseids.
Good night.
Coming up here on BBC 4 tonight, the heartbreaking story of Sophie Lancaster, kicked to death for looking different. Black Roses is next.